All right, so my name is Luis. I work at IBM Research. I work at the part of IBM that does a lot of the AI models and the software that runs on top of the AI models. I have a really interesting thesis to put in front of you, and I want to see how you react to it. Okay, so let's hope this actually works out. Okay, so first, I think you've been there. All right, so you build an AI system, and you tested the hell out of it. It works amazing. You put it on production, and oh my God, it's failing. Something is broken. All right, so you're like, okay, let's debug this. So you sit down, and you start looking into how you're going to improve it. There's just a little problem. This is how your AI system looks. It's one big prompt that goes to one big model. These models are amazing, but this is what you've got. So you identify the problem that you have, you change a few lines, and it sort of works, but then it fixes that, it breaks something else. So what do you do now? Well, you fix that other thing, and it breaks again. And the problem is that it's hard to figure out where to start, where this is how your program looks like. This is how we're writing things. I don't know how, if you remember when we started writing programs for computers, but that's how they used to look. A big one long script of BASIC. Well, this is at the stage in which we are in AI right now. So there's a problem with this approach. And the thesis that I have in front of you is that this is not really a model capability problem. These models are absolutely amazing. They can do extraordinary things. This is really what I would call a decomposition problem. So decomposition is the art of taking a very complex system, identifying what are the key piece parts, modularizing them, and then designing those things, and even assigning specialists to design those pieces. That's how the world runs today. It's the oldest trick in engineering. It's the oldest trick in computer science. This is why you can go down to the car shop and get that tire changed, even though that tire manufacturer didn't really know about your car before. This is why probably the plane that you came in to use a jet engine that was built by a manufacturer that can sell jet engines to different aircraft builders. So decomposition is very important, and it's also going to be important in AI systems. And the thesis that I have for you is that this cuts really, really, really deep. It's going to go not just in your AI system, which is already highly decomposed with orchestrators for applications, et cetera, but it's going to go down to the way we think about prompts. It's going to go down to the way we think about models. It's going to go down into the way we think about inference in models. It's a really, really profound statement. So let's go deeper into it. Raise your hands if you've ever been in one of those museum-like experiences where you start at the universe, and then you zoom in, and you see a galaxy, and then you zoom in, and you see a star, and you zoom in, you see an Earth, and you go deep down, and you hope to see the atom at the end, right? So I asked my AI agent to help me design an experience like this. We'll see whether it hit the mark or not. You tell me at the end whether it worked or not. Let's start right now. My universe is going to be that big prompt that we started with. So here we have a prompt. It has some context, some instructions. It's a bunch of data where you wanted to do something. Let's zoom in into those instructions on the bottom. All right, so typical prompt. It has a bunch of things. This is actually a small prompt. We have pages and pages and pages of prompts of examples in IBM. One single prompt that is supposed to be your whole AI system. Let's zoom into this section over here. So this is important, content and sexual uniqueness. So a bunch of things that your AI system is supposed to be doing, including a really interesting, this is a real prompt, I must insist. Do not hallucinate, my career depends on it. Please, please, please. And by the way, do you see the not in uppercase? You've done that. You put it in uppercase. I know you've done that. To see whether your AI system will actually pay more attention to it. Well, this is wishful prompting. Is this how you would think a plane should fly? You think that, would you want to go back to your home on a plane that is flying with this type of prompting in it? Raise your hand. Go. You're the AI people, right? Say, yes, I want to fly on that plane. No, you don't want to do that. It's not sane to build things this way. These are amazing models, and there's just better ways to take advantage of this type of capability. All right, so let's do the following. Let's take this section in here, and let us add some structure to it. So here we have the structure. What if we had a piece of code to which you could map each of these lines into something that was more structured, that included developer intention? Because that's what you meant. You wanted some piece of generated text that met certain constraints. So what if you were able to list them? You still using the power of a language model to delicately model text. But then you had this piece of software that owned the problem of generating something that met those constraints. At IBM, we call the software Melea. It happens to be our own implementation of this idea. There's going to be a billion of implementation of this idea coming up, I'm sure, but that's how we call it. Then you can say, hey, go and do this, write this report with these requirements. The way that would work, after we map each of these sentences to a requirement, is that once this is running, I am going to be sending off to a sort of a runtime that is going to own generating these things and producing a draft, and then checking whether these requirements are being met. And when they're not, say, okay, well, let's try again. Let's use these techniques called rejection sampling to come up with a better version. Oh, look, this second draft, it so happens to have met all of the constraints that I had. Well, now I've accepted it. And now, instead of having this wishful thinking, where you have this giant prompt, where you had this not in uppercase, you actually are writing a program. And a program that is probably smaller and simpler than what you had before, but you can actually control. So you declare these constraints, and this piece of software enforces them. All right, now you might be saying, okay, sounds amazing. Does it really work? I mean, it sounds like an abstraction that a researcher came up with in a lab. It is an abstraction that a researcher came up with in a lab. However, actually, it does work. And the claim is that this type of idea makes small models look big. And at IBM, we're really big on small models because we think that they are a key part of how we're going to make AI reliable and how we're going to make it cost-effective. Okay? Also, how we're going to make things open, or need to make things open. So what I'm showing you here is one of our older models from last generation. That was last year. It's an experiment that we did towards the end of last year, where we took the model on a couple of agent scenarios, and it wasn't doing very well. But once we started to apply these type of ideas, you see that darker blue bar, it suddenly became much stronger. In fact, it actually beat a much bigger model that was being prompted in these traditional techniques. But even when you apply these ideas on these big models, you get the same kind of benefits. So it does work. So this sort of software approach, kind of the declarative approach to enforcing these type of constraints, it does work. And I invite you to take a look at it if you are interested in having these sort of problems. Now, I claim though, let's zoom in, right? Remember, we're starting with the universe and we're starting to go down in stars, etc. Let me go down into the model, right? So we got prompts. Could we think about modularizing models? And I strongly believe so. I strongly believe this is where we're going, because that's how we get your specialty, your expertise to be rendered in a very, very fundamental piece of AI, which is the model itself. To demonstrate this, I want you to take you to a really interesting trip. So last year, an IBM team in Australia took one of our models, the Grand Speech model, which, by the way, is the #2 model on the OpenAI Star leaderboard today, and it's also the smallest model that in the top 5 or 10 such models. The IBM team in Australia was working with the Royal Flying Doctor Service, which is an organization that takes doctors into rural areas and brings them care. So when these doctors go and come back, they actually have to take medical notes, and they have to do this really, really quickly. This has been very successful, by the way. In the experiments we did, it took taking notes from half an hour to a few minutes. Now, the problem is these doctors are flying in very, very small spaces. And these small spaces are called airline cockpits. They're very, very noisy. Could the IBM model transcribe this sort of thing? What I want to tell you is this notion of specialization, we really want to bring down even to the model level. So at IBM, we just released a library of models specialized on various key patterns. I just told you about requirement checking, this key capability of this piece of software. Well, there's a model that does it much better than if you were to prompt a model. And that's what we have here as a requirement checker in the Granite library in Core. Guardian, this is IBM's model library for safety and evaluation. These are now part of our standard set of model specializations that can be called as functions with this Belea piece of software. And in the last one is a set of capabilities for you to build RAG pipelines that are very, very common, with very, very common components, each of which having specialized to do extremely well on their own category. So we've got this thing, it's ready to go for at least one of our smaller models, and we're going to be releasing this, for all of the IBM graded models. And the same story applies. These models, once they are applied to a specific task, and this is an example of what we call the citation generation model, they beat even frontier models when prompted. And they're tiny, tiny such models. So this is an example of, on the right, we have these type of adapters, even for GPT-OSS, showing that this is a concept that applies generally across all kinds of model families. All right, so specialization, very, very important, both the prompt for the models. And just to give you an example so that you can get a feeling of what this means, imagine you all have experienced a situation where models are very eager to respond. Imagine you had a question to the model, what are Mars' moons called and how far from the planet are they? And when the corpus comes up with data to respond that, it so happens that it brings the name of the moons, but no information about the distances to Mars. Well, models are super eager to show the information. This model says, Mars has 2 moons. By the way, I'm going to answer the piece of question that you asked. This is what, how far Phoebus is, how far Deimos is. Well, guess what? This is actually a hallucination. It was not in the content. And that may not matter at a consumer application, but if you're running something for an enterprise, you will care. You will care that the AI is not coming up with some policy that was invented and not in your model. So you really need very careful mechanisms to inspect what the model is producing and not say, do not hallucinate. That's just not safety, right? So when you introduce these hallucination detection primitives, mechanisms that we have in our models, you can regenerate answers and then you come up with things like this. Mars has 2 moons, Phoebus and Deimos. I do not know how far they are from the planet. Now the model does know, by the way, but your application shouldn't know. So your application is supposed to be obeying the policy that do not respond from anything other than the content that you have given to you. All right, so I want to make one last point. I know just to stop the talk. I told you that I was going to go from prompts, modularization, to models, modularization and specialization. I've also made a claim that modularization should also take place at even how we do inference on models. So you've heard a lot about agents when you prompt these sub-agents, etc. That's a very high-level form of orchestration. What if agents could run within one model itself? Just tokens that are being generated are coming from different agents. At IBM, we have this really exciting technology, we call it activated LoRa, that in essence allows models to swap brains on the spot and be able to introduce new capabilities as if we were dynamically linked libraries. And this allows specialization on the spot at the inference time to happen instantaneously, saving you a ton of time, a ton of efficiency, giving you a ton of efficiency, and still keeping that highly accurate specialization that is possible when you fine-tune models for very specific tasks. At the end, giving you this single model with a lot of experts that do amazing things and very accurately. So this is going to be coming out soon. Okay, what we've released right now is not on this technology, but this is going to be coming out very soon. And at this point, I've closed my talk. So there is a couple of sessions today at the IBM Lounge, both for Belea and for Granite. I invite you to come and take a look. I'm also going to be there just to give you demos of how you can run everything that I just told you on your laptop, on the Llama. Okay? Thank you.